again this IV equation that comes, then it will be clear. So this is simple current to voltage, current versus voltage axis. Okay, on the x-axis we are taking voltage, on the y-axis we are measuring current. Okay, IV characteristics means we are valuing the voltage and measuring the current. When there is no light on the device or solar cell, it is just like it looks like a simple PN junction diode. This is the dark characteristics. Okay, when there is some light on device, okay, extra electrons will be generated. These extra electron volts we are calling photo generated charge carriers or photo generated carriers. Okay, because of this extra charge carriers there is a extra current will flow in a circuit. That's why this curve will shift downside. Okay, just like this. Okay, second one is photo characteristics. First one is dark and without any light. Dark means without any light. Okay, photo means with some light. Okay, so on the voltage axis where we got the maximum voltage, that is open circuit voltage, and on the current axis where we got the maximum current, that is short circuit current. Or generally we will discuss this is as a short circuit density. Short circuit density means current per unit area, because always solar cells will take in a area. Suppose 10 meter square module, if you take how much it is converted into a electricity. That's why we will take always a current density, but here okay, no need, just you can go through like this only. No current as a current, okay, no problem. So this point where we get the maximum power, that point we are calling maximum power point. If you operate solar cell at this point, you will get the maximum power, or you can extract maximum power from the solar cell. Okay, here you can draw two lines to voltage axis and current axis. If you draw two these lines, this is V maxima, and here on the current axis I maxima. Okay, this is the simple IV characteristics, and we will go to the solar cell parameters. Already we have discussed yesterday solar cell parameters. We will go through again this, then you will be clear. Without writing the solar cell parameter, we will not get full marks. Okay, so to study the device, to understand the device, these parameters are the very important, because without these parameters you cannot judge the performance of the solar cell. First one, short circuit current or short circuit current density. Okay, whatever you can write. Short circuit current, that is ISC. Short circuit current is ISC. Second one is open circuit voltage. Open circuit voltage. This is VOC, open circuit voltage. We will shortcut, we will write VOC. Third one, fill factor. Okay, fill factor will indicate how efficiently we are extracting the power. How efficiently we are using the solar cell, that will indicate this using this solar cell. And fourth one, final one, efficiency. This is very important. If you estimate above three terms, above three parameters, you can estimate the final one, efficiency, that is eta. So finally percentage of light is converted into electricity, that we can measure using the efficiency. Okay, so yesterday also we have discussed this few terminologies. Short circuit current ISC is when device is shorted maximum, when device is shorted. Okay, shorted means we are just connecting, shorted device is shorting here. Devices we are connecting two terminals. When you connect two terminals, we'll get the maximum current flow. We'll get the maximum current flow, that is I maximum current flow will get, that is ISC. Okay, that is short circuit current we are saying. Okay, now we will see this one. We know total current is given by I dark plus, here total current, or you can write illumination current. That means when you illuminate light, there is a dark current and photo current. So that's why we are writing illuminating current, or you can write dark and photo, whatever you can write, is it is your convenient way you can write. So here you can write this expression, already you know this one, e to the 4 of QV by NKT, okay, minus 1, okay, minus 1. Here IPH we are writing photo current, that is we are taking minus sign because photo current is always opposite to the dark current, okay. So total current is given by dark and photo. Here dark current is given by I0 into e to the power of QV by NKT minus 1. Here IPH we are writing just IPH, that is photo current. Okay, this is total current. Now you come to the short circuit condition. When short device is shorted, okay, voltage is 0. When device is shorted, voltage is 0. This is the, you can see on the curve also, on the y axis, that is current axis, voltage is 0. Voltage is 0. So that's why you substitute this voltage in this equation. If you substitute voltage in this equation, you will get this term e to the power of I0 into e to the power of 0 means 1, that is 1, I am writing directly. 1 minus 1, this term becomes 0, then IPH will get. So total current in the device or total illuminated current is equal to the IPH. Maximum current will get the photons only, whatever photo generated current, the maximum current here, okay. ISC is equal to the IPH, okay. ISC is equal to the IPH, just minus sign indicates the, here we will take the third quadrant we will take, that's why it is opposite and we will take in a third quadrant, okay. This is the ISC, okay. ISC we have derived. So next one is open circuit voltage, VOC. When device open circuit voltage, in the question only you will have answer. When device is open, okay, device, we are opening device. Device is open means, suppose if you have a switch in our home, suppose if you have a bulb or any lamp, if you open switch, that means we switch off the bulb, that means no current will flow to the bulb, so that time bulb will not glow. So if you switch close means we are switching on, close means on, open means off, okay, that is you know. So when your device is on, maximum voltage drop, okay, maximum voltage drops across the device, maximum voltage drop across the device, that is what open circuit voltage means, okay. When device is open, maximum voltage drops across the device. This is what open circuit voltage. Here current is 0. Total current is 0 because device is open. We will not connect it. We haven't connected this device. So there is no flow of electrons. So here current will become a 0. So you can write total current is 0 equal to I0 exponential Q V, in place of V you write VOC. Okay, then NKT, okay, NKT minus 1, here IPH, right. So here just to, in open circuit condition we have substituted I is equal to 0, total current is 0 because device is open. After that, in this expression we are simplifying this expression, Q VOC by NKT minus 1 equal to IPH by I0, IPH by I0. So now you send this one also right hand side, okay, Q V0 VOC NKT by NKT is called IPH by I0 plus 1. So you simply apply here logarithmic, okay, or ln. So here finally you will get QVC by NKT, here ln of, okay, ln of IPH by I0 plus 1, okay, I0 plus 1. So this is expression. Here we further simplify this expression. VOC equal to NKT by Q, NKT by Q ln of IPH by I0 plus 1, IPH by I0 plus 1. This is the open circuit voltage. Just what we have done here, if you go through this again, open circuit voltage, the when device is open, we haven't connected the device, maximum voltage drops across the device, okay. In that condition total current is 0 because device is open, so you simply substitute total current is equal to 0 in the equation. Then after that you simplify this expression and you apply logarithmic, then you will get the VOC. Okay, VOC will depend mainly on this I0 and IPH. Okay, and also it will depend on temperature also. Okay, temperature, and actually VOC will mainly depends on resistance. Okay, resistance losses in a device. Okay, next thing we will see the fill factor and open circuit voltage. See here, on the open circuit voltage, on the voltage axis current is 0. That's why we have substituted there. Okay, next one, fill factor. Okay, what this will indicate? Okay, fill factor, third one. Okay. Okay, fill factor is indicates the ratio between I maxima and V maxima by ISC into VOC. ISC into VOC. So this fill factor mainly indicate the squareness of the curve. The squareness of the curve. Okay. Here see, suppose we are getting the, here if you see this curve, just I will say one more diagram. Suppose here we are getting, just I will try here only, I will down. Suppose here we are drawing a curve here. Okay, if this is the ideal characteristics of a diode or solar cell. Okay, this is current and voltage. Same. This is photocurrent. Okay, so this is ideal curve. But if you measure the curve will not follow this way. Okay, that case it may be following this way. That time here we are getting the first curve. In the first curve here we are getting the 100% conversion, but here there is some losses are there. It is not following the same curve. That's why it will indicate how effectively it is converting, how effectively the device curve is following ideal curve. Okay, that's why it is indicate. Here we are measuring the squareness of this curve. I maxima means this one, V maxima means this one, and I maxima means this one. So ISC, this is ISC and VOC. So the ratio of two squares we are measuring. Okay, ratio of two squares. Suppose here I am trying again. See this one. So like this. Sorry, just 1 second, please. Try a little bigger diagram. Then we'll. Okay. Fill factor will indicate, so take this one, current axis and voltage axis, and here drawing the only photo curve only we are drawing. Okay, this is photo curve. So this is VOC and this is I. Okay, next one, here we will get the power maximum. Okay, power maximum will get this point. Okay, at this point. Okay, at this point, this is power maxima or P maximum. Power is maximum here at this point. Okay, because at the VOC point, current is 0. Power equation is given by voltage into current. Okay, so if you take on the voltage axis or current axis, if you take voltage axis, current is 0. That means power is becomes 0. Or if you take on the current axis also, the power is 0. Only we will get the maximum at this point. MPP point will get the maximum power. So this is IM and this is VM. So here IS is measuring the first one. Thus, how much we have extracted power, that is curve 1. I am drawing curve 1, and how much actually curve is. Okay, suppose curve is getting this way, but power is, we are not getting maxima this curve. Okay, that's why it is measuring the ratio of first square by second square. Then we will see how much losses are there. We can measure using the fill factor. Suppose there is a resistance losses or any resistance losses are there, we can find out using this curve. So if there is any losses in the device, the curve will not follow the ideal curve. Okay, it will not follow the ideal curve. Suppose if you draw ideal curve, it will be like this. Okay, I am drawing this ideal curve. It is square, complete square you will get. But here we are not getting complete square. That means there is some losses in a device. Either defects are present in a device, or optical losses, all contact resistance losses, or interface losses, any losses. Okay, different kind of losses are there. Okay, because of these losses we will not get the complete perfect square. Okay, this will measure the how effectively fill factor mainly measures the how effectively the device is converting into a electricity, how efficiently it is using the power or how efficiently using the sunlight or light, and it is how effectively converting into electricity. That will indicates the fill factor. Okay, is it clear? Fill factor, how, what is the definition of fill factor? Just it is a ratio between squareness of the Im and Vm to Isc and Voc. Im is the maximum current and Vm is the maximum voltage. Maximum voltage in the sense you will get the maximum power here. Okay, maximum power. P maxima, Im, Vm, you can write P maxima by Isc into Voc. Okay, it will indicate the squareness of the IV curve. Fill factor mainly indicate squareness of the IV curve. Yes, squareness means how effectively the sunlight is converting into electricity. So if it is following ideal curve, we will get the 100% it is converted. If it is not ideally square, complete square, that means fill factor will be maybe 30%, 20%, or maybe like that 40, 50, 60. So that means it is not completely converting. Okay, if it is 100% only, it is converting. Next one, finally, is it clear to you if a fill factor definition and short circuit and open circuit? Is it clear, you guys, what we have discussed?
Yes.
And next one, okay, thank you. Next one, we'll go to the efficiency. This is one more important parameter. Okay, whatever, if you have a device, we'll say how much efficiency you got. Okay, if you use a solar module, suppose you are going to buy one module for your home, so they will ask, there is a, suppose in a module they will arrange very systematically these solar cells. Okay, they will arrange solar cells in a module. Okay, just like this. Okay, and they are interconnected one cell to other cell. Okay, they will interconnected, and you will get the, there is a plug and this thing, then you can use the sunlight. Okay, how much power is, once you shine the light, and how much you will get the power you can. So each cell having supposed 13%, 15% efficiency, or 20% efficiency. So depending on area and depending on material and depending on efficiency, the price of module will be changed. Price of module will be changed depending on efficiency of solar cells and materials. Which material is used, polycrystalline material used, or monocrystalline used, or pure crystalline used, or some other amorphous materials are used, or any organic materials are used. Depending on material, our module cost will change. Okay, this is why always you need to estimate efficiency. Then only, suppose if it is 20% efficiency means, what does it mean? Suppose we are getting 100% sunlight. Okay, 100% sunlight. From this 100% sunlight, these solar cells or these solar modules are converting into 20%. Okay, from this 100% light they are converting only 20%. Remaining 80% are not using. This is simply wasting. So our sunlight, we have sunlight, that is 100% light is coming, suppose. Okay, in that, if you use solar panel, if you keep solar panel, in that solar panel your efficiency is 20%. That means the solar cells or solar panels are converting only 20% of light into electricity. Remaining 80% sunlight is wasted. Okay, that is not using this solar cell. Suppose if that solar panel is utilize more light, then we can produce more current. That is what research is going on, using different materials, different architectures and different designings. Okay, they are doing this one. Now the definition of this one is given by total output or maximum output or total output power for incident power. So whatever extracted output power by, or you can write P output also, you can write whatever you can write, P output by P input. Suppose here input means from the sunlight we will get the general sunlight is 100 milliwatt for centimeter square. Okay. If you mount a solar module, if you install a solar module for centimeter square area, you will get 100 milliwatt power. Okay. This is the incident power per 1 centimeter square. The meaning of 100 milliwatt for centimeter square is you will get the 100 milliwatt power if you within a 1 centimeter square area. Okay, you will get 100 milliwatt power per square meter, 1 square meter area. That is what P input is. P input is this much. Okay, if you use this much light, how much light you are extracting, how much current you are extracting, that is giving by P maxima. P maxima. P maxima is how much power you are extracting from the solar cell. That is P maxima is given by V maxima and I maxima. V maxima and I maxima. This is the solar power. Okay. From this expression, the eta is given by P maxima by P in. Or you can write here eta is equal to efficiency is equal to P maxima is equal the fill factor. What is the definition of fill factor? Fill factor is equal to P maxima by ISC into VOC. ISC into VOC. Or you can write V maxima I maxima by V maxima I maxima by ISC into VOC. This is the fill factor. From this expression, you can write V maxima I maxima is called fill factor into ISC into VOC by P input power. P input power. This is another formula. Or you can write simply fill factor in efficiency is equal P output power by P input power. Or you can write P maximum power extracted power from solar cell to P input power. These are the definitions. Okay, if you know fill factor, if you know ISC, if you know VOC, and you can estimate the efficiency of the solar cells. Okay, these are the solar cell parameters. One is the short circuit current. Second one is open circuit. Third one is fill factor, and fourth one is efficiency. So short circuit current is when device is shorted, maximum current flows to the device, that is ISC. Okay, but at the ISC point, voltage is 0. So the power is 0 at ISC condition. Similarly, at VOC point also current is 0. That's why power also 0. But where we will get the maximum power? If you see curve on the IV curve at this MPP point, that is where you get the maximum power. Or at this point, you will get the maximum power from the solar cell, or you will extract the maximum power. Okay, that is what here. Corresponding voltage is the V maxima, corresponding current is the I maxima. Okay, so from this expression, short circuit condition means you have, voltage is 0 at this condition. You simply substitute that voltage and you will get the ISC is equal to the total photo current. And second one is open circuit voltage. When device is open, we are not connected terminals. Okay, in that case, total current is 0, but here maximum voltage drops across the device is the open circuit voltage. Simply you substitute I is equal to 0 and V is equal to V0, VOC. Okay, then you will get the VOC is equal to NKT by Q into ln IPH by I0 plus 1. Okay, N is the ideality factor, how ideally our curve is following, and K is the Boltzmann constant, T is the temperature, Q is the electron charge, pH is the photocurrent, I0 is the reverse saturation current. So reverse saturation current means that is a leakage current. If you draw the diagram, suppose you are getting this curve like this. Okay. Suppose this is a ideal. There is some loss. It is not following correctly on the y-axis. Okay. On the x-axis it is not following. Here there is some distance between the x-axis. That's why it is a some loss is there. Some loss is there because of maybe defects or maybe other minority or majority carrier diffusion. Okay. So always I0 should be less. Then only your VOC will be higher. VOC will be higher if I0 is lesser only. This is reverse saturation current or leakage current in a device. Leakage current should be always less. Then only our device will show good performance. Next one, fill factor. That it is ratio between P maximum to ISC into VOC. This will indicate the squareness of the IV curve. If square is perfectly, if fill factor is higher, then the curve is, it comes as a square. That means it ideally following the perfect diode curve. And also it is perfectly utilizing the sunlight and perfectly delivering the power. That it indicates. Okay. And final one, efficiency. This will give you the extracted output power to incident power. The ratio between extracted output power to incident power, P out to P input. From this fill factor equation or fill factor definition, you can modify the efficiency formula. Efficiency is equal to the fill factor into ISC VOC by P input. Okay, this is the solar cell parameter. Very important. You write the definition and equation. Okay, definition and equation. You have to mark the ISC, IM, VOC, VM on the IV curve. Okay, is it clear to you, everyone? Is it clear?
Yes, sir.
I don't know how many are listening. Okay. Anyway, so next one we'll see the small this thing, effect of temperature or resistance. Okay, suppose we have a device. Suppose this is current and this is the voltage. Okay. Suppose if series resistance problem is there. Suppose we are using different materials. Each material is having some resistance. If there is a series resistance, actually this is the ideal curve. Just we are drawing ideal curve. Okay, this is the ideal curve, just like this. Okay, so if it is series resistance, each VOC will affect. Okay, the curve will fill factor will affect mainly. So if here series resistance will affect the near the voltage curve. Series test, if there is a problem in series resistance or series resistance is higher, the curve shape will change at the open circuit voltage. Or if there is a problem in shunt resistance, the curve shape will change at the short circuit condition. Okay, this will maybe it follow like this. It may be follow like this. Or if it is more, series resistance is very less, shunt resistance is very less. Okay, series resistance should be less, and RS should be less, and RSS should be very high. Okay, then we'll have the good performance. If shunt resistance is decreasing means the curve shape will change at the near the current equation or like this. It may follow like this. Okay, because of the series test losses, the curve will shape will change. If shape is changing means the power will change, efficiency will change, and fill factor will change. Mainly fill factor will affect because of resistance losses. If fill factor is affecting means efficiency also affects. Okay, so each one is linked to the one another. Okay, this is a solar cell topic, and this here also you can like what we have discussed PN and PAN structure. Here also you can do it. This is N layer, this is P layer. Here you will have metal contacts. Here also you will have metal contact. This is just simple PN structure, and also you will have PIN structure also. PIN, because to improve the efficiency of solar cell. Okay, efficiency of solar cell. Down one is N, middle I, and top P. Here also you will have metal contacts, and downside also you will have the metal contacts. Okay. This is PN structure. Once you shine the light, electron hole will be generated here. But in PN structure, at the interface will be generated because of the electric field. Holes only go to the P side and electron go to the N side. Here also similarly, at the interface also generate electron holes. At the I layer also electron holes will be generated. So because of this extended electric field, more number of holes will go towards the P layer and more number of electrons go towards the N layer. So that here current will increase and open circuit will increase and efficiency also increase in PIN structure. In PIN structure the efficiency is low and PIN will get the high efficiency. Till now we are converting about 25% of sunlight. We are getting the efficiency of solar cells with the different structures. We are getting 25%. Okay, this is till now in market. If you go to the module purchasing module, they will module efficiency is about like 20%. Okay, about 20%. Each module having in a module cells in a module having 20%. They will arrange it in a systematic manner. Then you will get the module. Suppose 1 meter square area you want, or 2 meter square you want, or 100 meter square you want. Depends on your requirement. You can buy the modules. Okay. Suppose in 10 meter square they will arrange 4 modules. If 100 meter square they will arrange maybe 10 solar cells. Okay, like that. It depend on our requirement of area. You can install the solar cells in a systematic and you can interconnect that solar cells and you will get the total output power. Okay, this is the about simply solar cells. Okay, simply solar cells. Any doubts here? Are you having any doubts on this thing? And also you can see this one. Just I will show some animation for this. Okay, see, can you see this one? See, this is. Can you see this page? On page I displayed.
Yes, sir. Visible.
Yeah, okay. So this is simple solar cell. Okay, downside is metal contact and top side also metal contact. Then we have connected to load. Okay, and PN layers are there. Just you start. So we are shining some light. From sunlight is coming. So once sunlight is there, electron hole will be generated. Okay, red bubble is the electron and blue bubble is the hole. Okay, after generation at the interface we have a electric field. At the interface we have a electrons sending only n side. See, electrons going only n side, holes going down side. That means p side. So you got it. So this will complete. We will measure the current and we will use that current. Okay. So just see again this one. Just using sunlight, electron hole will be creating because of the internal electric field, and also this internal electric field we are extending or we are strengthening using reverse bias voltage. Okay, once we apply, only electron going inside and holes going p side. Okay, after that they complete the circuit. Okay, so that electron hole recombination also reducing and we'll get the power, or we will measure the current and voltage. Then we will see the how much efficiently the solar cells is converting the efficiency. Okay, this is the simple. This is simple one. Okay, now just we'll see one more thing. Hello, can you hear me?
Yes, sir.
Hello, can you hear me? So, can you hear me, right?
Yes, sir.
Yeah, only ISC is equal to IPH. Just I am writing solar parameters. Then VOC is equal to, you can write NKT by Q. Not visible. Okay. Now,
Now visible, sir.
yeah, okay. ISC we have derived this one. Okay, ISC we have derived this one. ISC is equal to IPH and VOC is, you can write NKT by Q into ln IPH by I0 plus 1, and fill factor, third one, fill factor can be written as, okay, I maxima and V maxima by ISC into VOC. ISC into VOC. This is the fourth one is efficiency. Efficiency can be written P maxima or P output power. Output power by P incident power. Okay. So here you can write this one from the fill factor equation, FF into ISC VOC by P in. Okay. These are the solar cell parameters. Just you can go through the once, then you will be clear. Okay. So today we have completed this third unit. If we get time on Monday, we'll solve some problems. Then we'll go to the fourth unit. Okay. Is it clear this third unit? Any doubts? Anything queries? Are you having any doubts here?